This is a great probability investigation that starts with this probability game using a 0 to 13 strip. You just need 2 dice, and then it's played between 2 players, each need 5 counters, each in the same colour. So to begin, players have to choose what numbers to place their 5 tiles. And if they want to, they're allowed to put more than 1 tile on each number. So if I wanted to, I could put 2 on 6, 1 on 8, 1 on 4, 1 on 10. So players will take turns rolling the dice, adding the numbers together. Then, if the players have a tile matching the number that was rolled, they're allowed to remove 1 tile from that. So, because I rolled an 8, both me and my opponent have 1 tile on 8, so we get to take our tiles off. And then the first player to remove all of their tiles wins the game. And if they were unlucky enough to place a tile on 0, 1 or 13, by this point they might have realised that those numbers are actually impossible because the minimum number we can roll on our 2 6-sided dice is a 2 and the highest is a 12. And you might be asking, well, why do I include those numbers on the strip? But that's because those are the conversations that I want to come out through playing this. But now's where the fun really begins, because after students have played that initial game and started to notice things, you're going to say to your class, all right, we've noticed that some of these numbers in the middle seem to be coming up a little bit more often. So we're going to collect some data to see if we can get a better idea of what's actually happening here. So then you're going to give each pair of students 50 Unifix blocks. And this time, instead of playing the actual game, they're just going to collect some data and they're going to roll their dice and stack the Unifix up behind the numbers until they've used up all 50 rolls. And so the coolest thing about this is you literally see a graph grow before the student's eyes and see the pattern slowly emerge. And so, after your 50 trials, you're most likely going to end up with something that looks a bit like this bell curve. Now, it doesn't always work out perfect. It's worked out quite nicely for me. 50 trials is a good amount. But then every now and again, you might have an anomaly where someone might, let's say in the number 6, have only rolled that 1 time. Because we know in data, especially with a small sample size, anomalies can happen. So then what I like to do is I like to get everyone to one at a time say, all right, everyone bring your 12 stacks down to the floor, and then combine everybody's data together to make one giant class sample, really emphasizing that bell curve. So then once you've been able to graph it all and make sense of it, now it's time to try and get your students and think, why is this actually happening? What is the reason that these middle numbers, the 5, 6, 7, 8, and 9 are coming up the most? And especially, why have I ended up rolling 7 the most times? So to answer that question, depending on your year level, it's really going to change with how much support you give them during this next step. But hopefully you end up with something like this, that shows all the different possible solutions we can get from rolling 2 6-sided dice. So for example, up the side here, I've got my blue dice, the 6 different numbers I can roll on my blue dice, and the 6 different numbers I can roll on my red dice. And from that you can see that altogether there's 36 different possible answers we can get. But then if we look at the actual probability of each number, well, here's number 2. Here we can only roll 2 if we're lucky enough to roll 2 1s. So there's only one possible way to roll a 2. But then here there's only 2 possible ways to roll a 3. We could roll it with a blue 2 and a red 1, or a red 2 and a blue 1. And then this continues. So there's 3 ways to roll 4 and 10. There's 4 ways to roll 5, and there's 4 ways to roll 9. 5 ways to roll 6. But then it becomes really obvious why we've got so many 7s, and it's because that 7 has a greater chance than any other number, because 7 is the only number with 6 different ways of rolling it. So again, depending on what we're trying to achieve and what year level we're working with, we could write all those chances as a percentage chance. So here you can see 2's got a 1 in 36 chance. To roll a 3, we've got a 2 in 36 chance, and then 7's all the way with 6 out of 36 chance. Now if we simplify that down, that's a 1 in 6 chance of rolling a 7. So then finally, after you've been through this with students and they can see why this bell curve is happening, then they can go back and play the game again, this time being more strategic and using what they've learnt to their advantage to see if they can improve their chance of winning the game, or at the very least, getting all their counters removed in fewer turns than they did to begin with. All right, go math it up.